Okay, we're going to go ahead and get started. The last thing that we talked about last class was the way that we had to modify TTT diagrams to have them reflect real life. In real life, we said you can't instantaneously change the temperature of things. Even if you instantaneously pulled it out of one furnace and put it into a furnace at a different temperature, your material's at that temperature, and the heat has to diffuse out of it. And we learned last chapter that thermal transport is not instantaneous. It might take some time. So because of that, it really makes much more sense, instead of talking about a TTT diagram where a temperature can change instantly, instead to consider these CCT diagrams. So again, on these diagrams, we basically said that these diagrams show you what phases form, how the transformation occurs. You still have the sort of nose of these curves, but now instead of having it assuming one single instantaneous rate, you've got different lines here that represent different rates of removing heat out of your material. And it's a much more realistic scenario. Okay? All right. There's very little left in this chapter, so we're just going to go briefly about it. One thing we should be able to ask ourselves is, what should the tensile strength, hardness, yield strength, all of these properties, what should they look like as a function of carbon content? As we move from steel that is just a tiny bit of carbon, like a 1010 alloy, all the way up to something that has lots of carbon, how should these properties change? And more importantly, why should they do it? So if we're going to plot the properties, let's say tensile stress first, as a function of your weight percent carbon in your steel, what should it look like? Go ahead and sketch it with your friend. While you're doing that, somebody had a question about homework. So there is no homework due this Wednesday. There will be essentially 2 homeworks due the last day of class. One is the crystal growth thing that you're working on now, and that's due the night before because it's a PowerPoint thing that has to have the audio. That'll be due the night before. And then in class, we'll have a homework, which will be the last written homework, which will have problems from both chapters 11, 12, and maybe 1 problem or 2 from sustainability or composites. So it'll be almost the size of a double homework, but you have 2 weeks to do it, so you have extra time. All right, how will tensile strength or yield strength or hardness all change with the amount of carbon? Anybody have a thought? What did your neighbor say? It wasn't even you. We won't even think that you're dumb. We'll think your neighbor's dumb. Or maybe your neighbor's brilliant and they got it right. So what did your neighbor say? Positive slope? Yeah, that's a good guess, right? It's going to increase. Now, why should it increase with a positive slope? What's the rationale? That's the harder part. It is the case. In general, these properties increase with carbon content. Why? How come? There's sort of 2 things that we could point to. Josh, what do you think?
So the carbon would create an interstitial that would inhibit formation of heat and increase the hardness.
Okay, let's go back to this. That right there is the austenite to martensite transformation. Austenite means at high temperatures you've got this FCC crystal structure, and the larger gray atoms might be your iron atoms. But you're exactly right. The carbon, the smaller white atoms, these sit at interstitial sites. So you see this sort of FCC arrangement, right? You've got like the 5 of a dice, right? This is on the face. You've got the corners. Well, this thing's sitting in between those at the interstitial, the carbon is. So the more carbon you cram in there, the more of these interstitial sites you start to fill. And therefore, making atoms slide past each other, it's crowded. The lattice is already crowded. So trying to make, I imagine you guys as students, right? If I took like an extra person and I put them in the middle of this row in an interstitial site, and now I said, okay, all you students, I want you to stand up and scooch over a chair, that extra person is messing it up. It's really making it harder for that dislocation to move. If you ever make a dislocation less mobile, harder to move, you made the material harder and stronger, right? So exactly right. That's one reason. Is there another reason? I should rephrase that. There is another reason. What is it? Why else are these things harder and stronger? Any thoughts? Does our phase diagram tell us anything? Increasing carbon content. What is the lever rule tell us about the two phases present and the amount of the two phases? Carbon content's going that way. So we're getting more and more of which phase? More and more cementite. I hear like quiet whispers. Why is everyone being shy today? Yeah, we're getting more cementite. Cementite, like its name suggests, is the ceramic. It's the cementite, right? It's hard and strong, right? So the fraction is increasing. If you increase the fraction of the ceramic, it's not surprising you get a harder, stronger material, but you're doing it at the expense of ductility and fracture toughness, so it's becoming more and more brittle. This is why when you go from low-carbon steels to medium to high-carbon to cast irons, you get stronger materials, but they get way more brittle. That's why you don't want to drop your cast iron pot, because it's more likely to fracture than it is to bend. Okay? All right. We will talk more about composites in 2 chapters, or 3 chapters really. After today, it'll be 2. Okay? All right. Yeah, question?
At a point of percent, does that line change? So if you have more carbon than other materials?
Good question. It does sort of plateau, and we're going to show you an actual plot in a minute, where it's sort of like you reach a point of diminishing returns, which is to say, you've already crammed so much carbon in the lattice, the dislocations are having a hell of a time to move. It's just really hard already. It's not getting any harder, right? And so you reach sort of diminishing returns. And really some of the most useful steels, they don't go that far into the carbon concentration. I think that high carbon steels are still, I can't remember, we talked about it recently, but a few percent is the limit, and you've already really hit your benefit limit. Okay? So what about impact energy, reduction in area, our ability to reduce it in area before it fractures, and elongation? Well, what should these be? Go ahead and sketch that with your neighbor. All right, what do we think? If you were going to sketch it, how might it look? Not a positive slope. How come? It will be negative. We're going to lose our impact energy. We're going to lose our elongation. And the reason why is it's the exact same reason as before. Dislocations can't move. We made it harder and harder for dislocations to move. If you want to elongate something, you're relying on dislocation motion. If you want to absorb a lot of energy, then you want plastic deformation during deformation, right? If it can't deform, you can't absorb a lot of energy, so you end up with a small impact energy. So the more and more carbon you get, it's gotten harder and stronger, but you sacrificed impact energy. Hand?
Yeah, what is meant by impact energy exactly?
So if we go back to chapter 7, I think it was. Chapter 7, we talked about impact testing, if I can find it. With the Sharpie impact tester. Oh gosh, where was it? Might have been deformation chapter. So impact testing, I'm not going to find it now. This was one where we took a pendulum, right? And you swing the pendulum, and if there was no material there, it's going to swing to almost the height that it started at, minus friction of the pendulum, right? But if you put a material there that your pendulum chops through, it won't swing up as high as it started. Maybe it started here. It'll only go that high when it finishes. And that difference in height times the weight of your pendulum, that energy, that potential energy, must have been, it didn't get deleted, it must have been transferred into your material during the fracture process. So that's impact energy, right? Is the fracture energy that occurs as you break a material. And I can't remember where we talked about that. Any other questions? Yeah.
So is that the same as when you drop a metal ball on metal plates?
Yeah. That's sort of it's a similar measure of it, right? When we had the atomic trampoline, one of them bounced like crazy because it wasn't absorbing energy. The other one absorbed a lot of energy because it dented the material. The reason that it didn't bounce up high was because it could impart energy by denting the material. If you make your material so hard that dislocations can't move, you can't dent the material, you don't absorb any energy. So when it does fracture, it's going to break like a ceramic, which doesn't absorb a lot of energy, which is bad usually, right? So here's actual curves to answer the question earlier. Is there a point of diminishing returns? Yeah. By the time this goes from 0 to 1%, 1 weight percent carbon, you're already sort of plateauing out in some of these. And then this shows the effect of different microstructures. So even at the same carbon content, right, at the same carbon content, you can see that different materials will have different values for their, this is showing Brunel hardness, which is one type of hardness measurement. Okay? Any questions on any of this, on how carbon concentration or microstructure changes behavior in materials? All right, so let me ask you this. Why is martensite so strong? We talked about this the other day, but why was martensite so strong and hard? What made it so hard? So remind your neighbor, if you remember, what was it about martensite that made it such a good, hard material? Okay, what do we think? I'm going to ask the striped shirt in the middle who's trying not to look at me. That's right. So what do we think? Why was martensite a hard, strong material? What was it about its crystal structure or this quenching process? Missed class last week. You have good news. The lectures are on YouTube, and you're going to want to watch those because this is what the final is going to be on. About half the questions will be on this new material. Somebody help him out. Why was martensite a hard material? Yeah, in the back? Yeah. When you elongate this, think of what that does to your symmetry, right? When you had a cubic crystal system, we said that the common slip systems in the FCC crystal were the planes on the 1-1-1 direction. Well, this is the 1-1-1 plane. Sorry, not the 1-1-1 direction, the 1-1-1 plane, excuse me, right? And technically, we could draw 8 different versions of that connecting different corners of this thing. But as soon as you elongate this crystal, when you elongate it, I'm going to super exaggerate it. It's not nearly this exaggerated in real life, but this makes it easier to see. And then we draw that 1-1-1 plane. It's very different if you pick different directions, right? That plane is now going to be very different than, say, the plane between the back of this crystal, this one, and this front plane. Right? That's a very different plane. So it reduces our slip systems, right? If you reduce the number of slip systems, you make your material more brittle, right? These dislocations can't move, so it got harder and stronger, but it became more brittle, okay? There's another reason why it gets harder and stronger, and it has to do with a volume change, right? The total volume is not conserved as you go from austenite to martensite, right? In fact, because of this change in volume, that leads to local stresses in your crystal as the transformation takes place, and those stresses are accommodated by microcracks. So you form all these microcracks in your material, which actually makes it kind of weak. It's filled with these tiny cracks everywhere, which is why they always follow martensite with a post-martensite quenching tempering, right? They temper it. We've talked about tempering in this class. A tempering is just a heat treatment that's intended to recover some of your properties a little bit, right? So to recover some of these internal stresses or cracks, they do a tempering. And the temperature at which you temper it at will change the microstructure. Not surprising, right? You start out, you have basically a single phase, but with cracks in it. You want to convert that to, remember what tempered martensite looks like. Tempered martensite doesn't look like a single phase anymore. It's one that we said looks like microscopic zebras, right? We've got the big fat zebras, we've got the small zebras, and these are like our microscopic zebras, right? The two phases do separate. When you heat treat it, you allow the two phases to segregate. But because it's happening at a low temperature, they really don't segregate very far, which gives you a nice mix of toughness and hardness. So that's tempered martensite. So there's something you can do which is called differential tempering. Differential tempering is kind of interesting. It means that when you heat treat your sample to do whatever to it, to add some ductility typically, you make it so that your sample experiences different temperatures, or at least different temperature rates, right? So for example, on this sword that they did here, they intentionally tempered different parts of the blade at different temperatures. Maybe your furnace has a gradient of temperature in it that you could do, or maybe you're doing this by hand with a blowtorch. So I've got a hillbilly brother who has got a show on Discovery Channel, and one of the builds that they're doing for these giant monster trucks they build, I should preface this. Let me explain who my brother is. First off, he goes by Heavy D, which tells you all you need to know about my brother. So this is my kid brother, who outgrew me within the first year of his life. But he was just recently doing some tempering, even though he's not a material scientist. He was doing this same thing. He started out with a clean metal that had been polished, and he was by hand blowtorching it, different regions to be different heat, so that they would change color in different ways, right? And you can do that to control the color, but it'll do more than just control the color. It'll change the properties. Now, why is the color changing? Did I put it on here? Oh, good, I didn't. Why on earth is the color changing, right? Take these different, I don't know what these metals are, probably, yeah, steel, right? And you put them in furnaces for the same amount of time, but different temperatures. Why on earth is there a temperature gradient or a color gradient there? What's going on? Anybody? Anybody feeling brave? Good guess. It's related to diffusion. It is related to diffusion. Why should the color change? Next chapter is a sort of preview to this. Next chapter we talk about electronic properties, and optical properties often are related to electronic properties. Why would the optical properties change? Yeah, what do you think?
Different microstructures or
Yeah. Everything that we've talked about in this chapter would suggest that, but it's not actually the microstructure. That's a great guess. It's a really good guess. Yeah, you might imagine like as the zebras go from microscopic to big and fat, maybe there's a color change. That's not actually what's happening here. Was the hand over here, Ashton?
the frequency the electrons are vibrating at different at those different temperatures?
Good. Oh. So it doesn't have to do with electron vibrations. It does have to do with electrons and their ability to move in response to light. That's a good guess. So this has all to do with the oxide that forms. If you put a metal in air in a furnace, an oxide is going to grow, and this is actually a function of the thickness of the oxide. So you get interesting optical effects as this oxide grows to really thick layers. If it grows really, really thick, it starts just being ugly. But in these intermediate regions, it grows to regions where light interacts in different ways because of boundary conditions of how thick it is. So we will talk more about this next chapter. Okay, then the last thing I want to say about this before we move to electronics is there's something called precipitation hardening. So we talked at great length about steels because steel is such an important material. We talked about how you quench it, how you change its composition, all these things. Just be aware that there's lots of other metals that are important, and if you want to strengthen another metal, and that metal doesn't have an austenitic to martensite transition, are you stuck with just a weak metal? No. You can make it a hard metal all the same, and here's how you do it. Precipitation hardening is one of the most common ways to strengthen an alloy or metal. Here's how it works. We go back to our binary eutectic phase diagram, our old friend, right? If you're right here, you have a single phase of what they're calling K, I guess, because they're barbarians and they started with K, right? So you've got K, and it's going to have grain boundaries, right? Some amount of grain boundaries, but it's a pure phase at some composition. If you cool this thing down rapidly, if you were to quench it, it's just going to look like K still, right? It'll just be a metastable phase preserved at room temperature. Because we know that this is a two-phase region, but if you quench it, you're going to keep that pure K. Well, what if instead of quenching it, you cool it down really slowly? What if you cool it down and you hold it right here below that temperature? Well, if you hold it there long enough, it's going to transform completely to now K plus epsilon they have written. So two phases, but you're going to have really coarse grains, right? Because it's at a high temperature, relatively speaking, and it's quite a long time that you held it. Well, what if you quenched it and then you heated it back up, just like with tempered martensite? You will precipitate out this theta phase. And because you're doing it at a lower temperature, you won't allow it to diffuse very far, and so your precipitates are very fine. So if you look at the microstructure, quenching it still basically looks like K. If you age it for a long time, you get really big globs. And if you just, this is if you age it too long, you get it everywhere. This is a less of an aging. I don't think these are the same zoom, but you get small regions, right? And if you have just a few small regions, that's precipitation hardening, right? So because of that, there's typically a curve that looks like this. If you're looking at the hardness for some alloy as a function of time at a fixed temperature, you're just going to leave it in there. If you could, put a robot inside that furnace and measure its hardness periodically, it might look something like this. It'll get harder at first, get a little bit harder, and then eventually it will decline. This decline is the only thing that we're really equipped to talk about in this class so far, and this is due to overaging, where basically your precipitates clump together, and as they clump together, they now are no longer doing as well of a job of restricting dislocation motion. So in this region, they keep on making it harder and harder for dislocations to move, but after a certain point, it starts to tail off. So again, you might think of this in terms of an application. If you're going to use a piece of metal for extended periods of time, the hardness, the strength, the ductility, all of these properties are changing because your ability to change dislocation motion is changing in real time. So again, you cannot go off of the spec sheet for room temperature. You have to look at tests that have been done at prolonged times at high temperatures. Okay? So why is it that precipitates make it harder for dislocations to move? I'm going to zoom in on this. It has to do with something we talked about earlier in this class with a single dislocation. We said a single dislocation looked something like this. You had these rows of atoms, you had extra half row, then you had this going on. Eventually, far away, it looked normal. So in the vicinity of that extra half row, you had the tension and you had compression. Right? You had like tension, you had compression. And so because of that, another dislocation, sort of those strain fields interacted with one another. Well, with a precipitate, you also get strain fields, right? So let's say this is a random alloy, and if you hold it at some temperature for long enough, a new phase is going to precipitate out. And you can see it right here. Here's our new phase that precipitated. But what we don't necessarily have to have is a coherent boundary. If you remember from a couple chapters ago, we talked about coherent versus incoherent boundaries. A coherent boundary is when these lattice parameters match up just perfectly, whereas an incoherent means they don't match up. So this is a coherent boundary. It sort of matches up, whereas this one, you can see that there's 1, 2, 3, 4, 5, 6, 7, 8 of the yellow atoms on the side, but there's only 1, 2, 3, 4, 5 of this new phase. Like the lattice parameter is different. And so depending on what you're growing, if the lattice parameter is very, very different, you end up with an incoherent boundary. If you end up with a coherent boundary that's just stressed a little bit, these are going to have different strains on the lattice around them, right? The surrounding lattice all around this is going to be strained in different ways, right? And if you age this too large, then you change that strain around your precipitates in either a positive way by increasing it or in a negative way by losing it, okay? All right. I think that's almost the end of this chapter. We've already talked a little bit about polymer transformation. We talked about crystallization. Just be aware that there's other transformations that can take place in polymers. Crystallization is the most common, but melting, the glassy transition temperature, these are all transformations that you could also monitor and approximate with Avrami kinetics in the same way that we did crystallization. Something that is interesting that you can do is you can actually measure the glassy transition temperature of a polymer, which is important for a lot of applications, using DSC. DSC or specific volume, either of these will measure it. DSC is a way of measuring the heat change in material. We talked about specific heat earlier in this class. If you looked at the heat flow into your material as a function of temperatures you heat it up, if there's this sort of bend in it, this bend in it is often associated with the glassy transition temperature. So for those that asked earlier this semester, how on earth do you measure this glassy transition temperature? How do you define when it really starts to go from like a ceramic to something that's now rubbery and plastic? You can measure it in a DSC curve where you see this sort of bend in the curve. Okay? All right, any last questions on kinetics before we move on? Trying to clarify anything about microstructures, about kinetics, nucleation, growth? Okay, let's move to electronic properties. So to start electronic properties, we've got our learning objectives for this. We probably won't get through all these. But we'd like to talk about electronic conductivity, and we want to do it in the same way that we've talked about, say, thermal conductivity or mass diffusion, and that is we're going to write it in terms of a flux of something in response to a driving force, okay? The flux of something in response to a driving force, and the constant of proportionality, that will be our electrical conductivity or resistivity, depending on how you want to think of it, right? We're going to differentiate between what's called the total resistance and the individual things that affect the resistance of electrons through a metal. We'll talk about calculate heat change. Yeah, we'll calculate something called Joule heating. As you pass current through something, it heats up that material. And we might get into band diagrams before we run out of time. That's probably as far as we'll get today. So let me start with an interesting demo. I've got here a material, a device, I should say. This device is 2 ceramic plates, right? And in between them, you've got a bunch of little metal, they look like pillars, right? And they're alternating. They're really small. They're not metal. These are semiconductors. And semiconductors are going to be a major part of what we study in this chapter with electronic properties because they make possible all the gadgets that are in your pockets, right? It's semiconductors. Not metals, not ceramics, but semiconductors. And we got real creative with the name. A semiconductor kind of conducts electricity, right? It's semi-conducting, right? So inside of this, what these can do, if you have what are called N-type and P-type semiconductors, and that just means that one has an excess of electrons and one has a deficiency of electrons, and therefore it has extra holes, right? If you put those together in a special way, you can make pretty cool devices called thermoelectrics. Can I have you hold this, Elias? So he's going to hold this between his fingers. I'm going to take a battery. Hope this one works. I've got a few backups. I'm going to connect positive to red, negative to black, and he's going to tell me what he feels on that. What do you feel? Which side? The thumb side? So the thumb side's getting warm. I'm going to reverse it. The other side's getting cold. When I reverse it, what do you feel? Exact opposite. It's instantaneous. There are no moving parts in this. There's no refrigerated fluid going through it. There's no compression of gas and expansion of gas to... That's how all of your refrigerators at home work, is using that basic expansion of gas cycle. This is completely different. This is what's called solid-state refrigeration, or a Peltier cooler. I don't know if we've talked about it yet in this class, but these things are pretty amazing. Anytime that you've driven in a car and you can have like heated or cooled buns on the seat, like they're using one of these. They've got it embedded underneath the vinyl or the leather, right? So what's cool about them, obviously, like they can do this little niche application where it pumps heat from one side to the other, and it does so instantly without any moving parts. That alone is pretty cool. But what I think is the coolest part of these is that you can run these in reverse. You can run these in reverse. Oh, I did talk about these when I talked about... No, I didn't. You can run these in reverse. For example, if I take this and set this on the table is colder than my body. So if I put my hand on the top of this thing, I've created a temperature gradient across it. It's not a big one, but it's a temperature gradient. So the same exact effect, the same exact materials, when I applied a voltage, it created a temperature gradient. What do you think I've created now? I've applied a temperature gradient. What do you think I've created? A voltage. I've made a battery out of my body, which is pretty rad. You guys aren't even impressed. This is amazing. This is amazing, right? What could you do with this? Let me ask you this. You've got these things. I give you a huge amount of them. What would you do with them? Where would you capture waste heat? Talk to your neighbor and tell him, where would you capture that waste heat to turn it into electricity? What would you do with it? Power pot. What's that? I was on 2 episodes this year. I talked to him about having another show with it. They were coming up with crazy ideas, though, like things I'm not sure are even possible of doing. They're like, you can make that happen. And it's like, I don't know. Although having it fail would be just as funny as anything. Okay, where would you use it? You've got endless what are called thermoelectric. We got real creative with the name. It's got electricity. It's got thermal energy. Thermoelectric. I give you endless of these. What do you do with it? Where do you put them? Yeah, Ashley, where do you use it?
A lot of, when you're burning fossil fuels, there's a lot of heat that's lost just into the atmosphere because you're boiling water that's with the turbine. You put these around the actual heating process, and as heat escapes, you could absorb some of that heat into electrical current instead of just letting it be lost.
Yeah, I was hoping for something better than a terrible diagram, but this is called a topping cycle, right? So you've got like your power plant, like a Rankine cycle or whatever. If you do something with that waste heat, that exergy, right, you could turn it in, you could improve the overall efficiency. So a topping cycle, yeah, you betcha. What else would you do with it? Hand over here.
To put it in a nuclear submarine, use the cold ocean as a hot reactor.
Yeah. What if you have a nuclear, like an isotope? In fact, there's a name for these. They call them radioisotope thermoelectric generators, RTIGs, right? So the radioisotope, that radioactive decay is a hot process. Neutrons are flying through, alpha particles actually are flying through, crashing into your material and generating lots of heat. So they're hot all the time for like millions of years, right? And you've got the cold ocean, so you've got a temperature difference. Bam. Put a thermoelectric between those two and you can generate electricity. That is how the Curiosity rover on Mars is getting its power, right? Is with a radioisotope thermoelectric generator. Anybody who read The Martian knows that because he wrote a legit book, which is fantastic, right? Okay, what else? Where would you use this thing? Where would you use it? Where else is waste heat? In submarines, apparently, on radioisotopes, right? In topping cycles. Where else? Andrew, where would you use it?
The body gives off a lot of heat, so you can use it in clothing.
Yeah, I tell this every year, and no one's invented it yet. You guys got to get on it. I want thermoelectric clothes. I want to, instead of just putting my phone in my pocket, I want to like plug it in so it's charging from my body, right? It's 2018. That's not too much to ask. What else? Where else are you going to use it? Anything? Have we run out of ideas? Josh, what do you got? Yeah. I don't know if I've talked about this or not, but in your car, when you buy gasoline, how much of that energy moves you forward? We talked about this. 20%. 70% is heat. 30% in your radiator, 40% in your exhaust. Why not take the advantage of some of that? In fact, if you could generate enough electricity to replace your alternator, so you don't need an alternator anymore, that's 5% on average. Depends on your vehicle. It's about 5% of your mechanical energy that's getting siphoned off to run that stinking alternator. So replace it with these things, right? So we could go on, right? Now the next question is, this is sort of voodoo magic. There's no moving parts. It's just a bunch of little legs squished between two ceramic plates. How on earth does this thing convert between heat and electricity? That's crazy. How is that doing that? Or equally crazy is a solar cell. Why is it I can take a chunk of silicon that's been doctored a little bit, put it in sunlight, attach a couple wires to it, and out comes an electrical current, right? Why on earth, when sunlight hits that thing, should electrons feel any motivation at all to move from one side of the panel to the other? Because that's what's happening, right? You have wires connecting the top and bottom of that thing, essentially, and those wires want so badly to go from one side to the other that they're willing to travel through your electronic devices and power them to get to the other side. Right? That's what's happening in a So why? How do we understand these things, right? That's what we're going to talk about this chapter, okay? And, you know, I barely have to say this, but some of the most exciting things, some of the best paying jobs, some of the most mind-boggling applications are coming with respect to electronic materials and material science. Things that do things that you would have never dreamed, that our grandparents would have said, nah, that's not going to happen. That's what's happening right now, but it often is to do with electronic materials. So let's start with electrical conduction, right? Let's go all the way to the basics. We want to describe how electrons move or don't move through a material. So this is a flux of something. It's not a flux of mass, and it's not a flux of heat, although electrons do carry heat. It's a flux of electrons, right? So we need, since we're talking about a flux, our old equation from before, we said, you know, a flux is always something multiplied by a constant, multiplied by a driving force, right? D something, right? A change, something changing with respect to either position, typically with respect to position, if it's fixed first law, right? Or time, if we're talking about fixed second law. So what is it for electrons, right? With mass transport, it was the diffusion coefficient, and the driving force was concentration gradient. With thermal transport, it was thermal conductivity, and it was the thermal gradient, right? Well, what about electricity? You guys, if you think way back to high school, you probably saw that V equals IR, right? Or if we rewrite this in terms of the thing that's moving, that's the current, I equals V over R, right? Well, that doesn't really look a lot like what I've just been describing. That doesn't look like a flux, doesn't look like a gradient yet. So we need to massage this a little bit to make sure that it works, right? So first off, what is current? Current itself has the units of amperes per meter squared. That's the units of current, right? And an ampere is just a number of electrons multiplied by their Coulombic charge, right? So this is basically saying some amount of electrons that are going to move through material per area squared. So all we need is time there, and that gives us flux. Because remember, flux is the amount of something per area per time. So we're almost there. If you did I divided by time, did I mess this up? Oh, no, I'm right. I'm wrong. Electrons is coulombs per second. An amp is a coulomb per second. So time's already built in. So I is already a flux. Current is already a flux. It's the amount of electrons per area per time. Okay? So what's the driving force? The driving force, anybody who knows like this battery, what is this battery? This is just a difference in electrical potential, right? You've got a voltage, it's a 9-volt battery, so it's got somewhere around 9 volts, depending on how discharged it is, right? And between these two ends, you've got a difference of 9 volts, right? So if you've got a difference between them, depending on what you put it through, if I hook it up to this thing, there's some physical separation between the top and bottom. If you take a difference in voltage divided by a difference in length, that's an electric field. So that's the driving force. This right here, this electric field, that's our difference in potential, right? So they're using phi in the book for voltage. That's your voltage. So you could say like 9 volts divided by 1 millimeter. That's our electric field. Okay. So we've got a driving force. We've got a flux. All we need is a constant of proportionality. And this time, the constant of proportionality is just the electrical conductivity. It's what gives us the right units and the right number when we hook up a voltage on something and we want to measure the current that travels through it per area per time. Okay. So the electrical conductivity is usually written as sigma. Sorry, I know that was also strength and a number of other things, but that's the unit that they use. And it has the units of Siemens per meter or inverse ohms per meter or mhos per meter. we got real creative with this one. We went with 3 different ones, right? The problem with it is inverse ohms per meter is the one that makes the most sense. But they didn't want to have like inverse ohms as its unit. So they made up a new unit where a Siemens is equal to an inverse ohm. Or, I don't know who came up with this one. They said, well, let's just spell ohm backwards. Mo. I didn't do this. Don't blame me, right? That's all the units of electrical conductivity, right? So conductivity, that's different than the overall conductance. It's easier to think of this in terms of resistance. So we're going to switch this. We're going to take our conductivity and we're going to flip it. 1 over the conductivity should give you the resistivity. This is easier to think of because you guys are already familiar with resistors, right? If you've taken ECE or even a high school physics class, you probably were given a resistor at some point. 10 kilo ohm, 1 kilo ohm, whatever these, it's great. It's got the different colored bands on it. That is a total resistance. It's a net amount of resistance to electrical motion. So if you take that exact same, anybody taking ECE right now, raise your hands. Okay, if I do this, tell me what I get. If I take one resistor like this, and then I connect it in series with another resistor like that, let's say this one's like 1 kilo ohm, and I've got 1 kilo ohm, what would be the resistance of end to end? 2 kilo ohms. It's not surprising. These things add up, right? It's some measure of difficulty to travel through that first one, and then you have to travel through the next one, so you just add those things up, right? Or in other words, if I had taken that little piece of, it's mostly a ceramic on those things, if I had taken that ceramic and I just made one that was doubly long, I would have doubled the resistance, right? So because of this, the geometry of your sample indicates that's related to your total resistance. Anytime that you have geometry into it, it's messy. We'd like to be able to calculate it without knowing the exact geometry, so we need a new unit. We need the resistivity, right? Not just the overall resistance, okay? By the way, resistivity, electrical resistivity, just has the inverse units of what we had for conductivity. So now it's ohm meters, right, is the most common way of presenting it. Okay? So this is what I was describing just a second ago, is these 2 expressions. These 2 expressions relate the electrical resistivity, which is a fundamental materials property, with the overall resistance, which is the device that you use in your electronics box, right? R is your total resistance, 1 kilo ohm, 100 kilo ohms, whatever it is. The resistivity is related to that if you know the dimensions of your sample. And this is assuming a really simple geometry, like a rectangle. So you've got a cross-sectional area, and you've got a length. So if you've taken Arne Stolp's class, he goes over this in a great way, but he describes electrical conduction as if it was like fluid flow through a pipe. If you want water to flow more easily through a pipe, you want a short pipe that's extra fat, right? It's the same thing with this. If you want electrons to be able to travel easily through this material, you want a large cross-sectional area, as big as possible, and you don't want it to be very long, okay? And that's why the resistance is inversely proportional to the area, but proportional to the length, and proportional to the resistivity. So if you take a material that's just fundamentally more resistive, like ceramics, right, it's going to give you a higher resistance. If you take something that's less resistive, like, say, copper, you're going to get a lower resistance. That's why we make wires out of copper and resistors out of ceramics. Because the resistivity, this rho value, is different for different materials. And it's different for different materials as you change the microstructure of those materials, or as you change temperature, right? So resistivity is not like a flat value you can look up, like, oh, steel's resistivity is such and such a value. The correct thing would be to say the resistivity of steel at this temperature, with this grain size, with this doping and all this, that is some value, right? Because it all depends, okay? Okay, once you know resistance, right, if I give you any arbitrary geometry, you can calculate the resistance. You say, oh, great. Resistance, as long as you tell me the resistivity, you tell me how long this thing is, what the cross-sectional area is, I can tell you what the total resistance is. What do we do with that? Well, the first thing that we might care to do is think about Joule heating. Joule heating means as you pass electricity through a wire, it's going to heat up. We showed this with the iron wire demo, right? We had the wall outlet giving us 120 volts. That 120 volts was then clamped across the wire about a couple meters apart, and then we alternated that current. So if you take the 120 volts and divide it by a few meters, there's some electric field across that wire, and then we're alternating that, and the strength of the electric field tells you how much your electrons want to travel back and forth, and we're alternating it, right? And so these things are going back and forth, and this is really, think of it in terms of collisions. They're occasionally going to be crashing into atoms and giving off some of their energy to those atoms. So then the atoms start to vibrate. And that is a local measure of temperature, right? So it's going to heat up. As you pass electrons, as they go colliding through your material, bouncing into atoms, they're heating your material up. And how much they heat up? Well, there's a simple sort of expression that is this. Q, the amount of heat generated, is equal to the current squared. It's really, I shouldn't say equal to, it's proportional to. This is just sort of a ballpark estimate. It's proportional to the current squared. So the higher the current, meaning you used a higher voltage and you got more current moving, you're going to get more heat, squared, multiplied by the resistance, multiplied by time. So resistance is in there because resistance to electron motion, that's kind of related to the rate at which it crashes into atoms, right? So again, if I took like a bowling ball, and imagine I took this bowling ball and I start trying to roll it up this classroom, it's going to start hitting some feet in the room, right? And the more feet that it hits, we'd say that it is more resistive to the bowling ball motion, right? But if you guys didn't want to get hit with a bowling ball, you might lift your feet up, and now it's less resistive. So that's going to travel through more, right? But every time it collides with somebody's feet, that heats you up a little bit, right? So if your thing is more resistive, that's more collisions, that's more heating, right? Analogy. I use it every year, and I always think I shouldn't use that analogy because I don't think it helps. And then I do it again. So sorry for the bad analogy, but that's resistive heating, right? So this actually came into play the first year that I did my iron wire demo. Every time I did that demo, I blew the circuit breaker in the room and the lights went out, and it was like a big snafu because I was making a mistake. I was buying just wire from Home Depot, and Home Depot, when they sell iron wire, it's huge. It's super high gauge, right? So I was using somewhere up here, really thick wires, because that's what I could get a hold of. So think about that. If it's a large cross-sectional area, then what have I done to my resistance? It went down. Higher cross-sectional area makes your resistance go down, right? So because the resistance is low, and the voltage from the wall is not changing, that's 120 volts no matter what, right? Then what's happening is that I'm getting more or less current. When the resistance is low, do I get more or less current? More current. How much current can these walls give us? Depends on when it was wired, when it was made, but probably 20 or 30 amps. And then it's got what? It's got a fuse, right? You trip the breaker because we don't want to pass so much current through the wall that those wires melt or catch on fire or burn this place down, that they built in a safety precaution because morons like me bring in huge gauge wire and say, just give it hell. I try and just give it as much current as I can, and it would heat up to the point where it would be unsafe. So instead, I tripped a breaker. And I was trying, because I'd seen this on YouTube. I was like, why can't I do this demo? I want to do it so badly. And it wasn't working. So I wised up and said, I'm tripping breakers because my gauge is too big. So I moved to really small gauge, which I bought at a sewing shop, right? Which was fantastic. I was trying to describe it to the person what I was using it for. Lost them instantly. Right? But he used a smaller gauge wire, and now it's got a much higher resistance. So for the same voltage from the wall, higher resistance means you're using less current, means you're not going to trip your breaker. And it's better. It also means that, right, you're going to generate heat. You're going to generate less heat because of your resistance, but you can change the distance that you clip these things apart to make R whatever you want. If you want it to be really big so you get lots of Joule heating for the same current, great. Clip them as far apart as possible, right? I mistakenly tripped another breaker recently because I had them not so far apart, and it pulled too much current because the resistance was low. But you guys see the relationship here between Joule heating, resistance, resistivity? Any questions on this? Okay. So I think we're going to... What do we do today? Let's see. Okay, we'll do this last example, and we'll save band diagrams for next class. So let's do this example together. So the question is this. How much heat would be generated if I passed 15 amps through a long rectangular sample of copper, which has the dimensions 3 millimeters by 4 millimeters, and it's 10 millimeters long, so it's sort of matchstick shaped. We're passing it along the matchstick shape. We send that for 1 minute. We're going to assume that the copper has a constant electrical resistivity. Why do I have to state that? Because typically, if something heats up, its conductivity changes. We're going to assume that it doesn't change because we're not heating it up that much. Okay? So this is a constant value. I want you to give me the answer in millijoules, rounded to the nearest millijoule. And recall that 1 ohm is equal to a joule per second per area squared. Let me pull up this question. Wrong one. Okay, in the 5 minutes left of class, let's give this a shot. So I'll remind you that when we're calculating heat, we're using that Joule's law expression, Joule heating expression, which is that Q is proportional to I squared times R times T. We're going to right now assume that it's just equal to it. We're going to just approximate it, okay? So Q, the amount of heat that's generated from the electrical current, is equal to I squared times R times T. Sorry, this is not area here. I said that wrong. I said that is area, but that is amps, amperes. That is not area. So the other thing to remember, if you've forgotten, is that resistance, the total resistance, is going to be proportional to the resistivity times length divided by area. That's our total resistance. Oh. Okay, so let's get your answers in. We're almost out of time. We've got resistance, which I solved for you. So just punch that into your Joule heating, get your questions, and then we're done for the day. Okay, get your answers in. Another 30 seconds. We're going to wrap it up. Okay, we're going to close the poll. Okay, people think this is the right answer. So about half the class got it right. We'll pick up here next time. Oh, wait. Yeah, that's right.